For the next subtopic for kinetics of a particle, which is about force and acceleration, is we will talk about the equation of motion, which is focused on the dynamic equilibrium and also on the system of particles. So first, we will discuss about what is the equation of motion, and afterwards, the definition of the dynamic equilibrium, and also how we apply the equation of motion in the system of particles. So for the equation of motion, when more than one force acts on a particle, the resultant force is determined by a vector summation of all the forces. So that is, the resultant force is actually equal to the summation of all forces acting on the particle. And for this more general case, the equation of motion may be written as the following. So this is actually the same of what we had discussed last time, which is the force is equal to the product of the mass times the acceleration, which refers to the Newton's second law of motion. So in this one, that is the summation of all forces acting on the particle is equal to the mass times the acceleration. So the same thing, force and acceleration are both, or it is in the boldface letters. Therefore, both of these quantities are vectors, meaning they have both magnitude and direction. So to illustrate application of this equation, we consider the particle shown. So this is the particle. And on the particle, we have actually two forces acting on it. We have F1 and F2. And the movement is going to the left. So as shown in an arrow, so it is accelerated to the left. And what we have here is an illustration which defines the free body diagram and also the kinetic diagram. So it can graphically account for the magnitude and direction of each force acting on the particle by drawing the particle's free body diagram. And since the resultant of these forces produces the vector MA, its magnitude and direction can be represented graphically on the kinetic diagram. So the kinetic diagram pertains to the particle's motion as caused by the forces. So the equal sign written between the diagrams symbolizes the graphical equivalency between the free body diagram and the kinetic diagram. That is, the free body diagram represents the summation of all forces acting on the particle, and the kinetic diagram represents the product of the mass and the acceleration. So for the equation of motion, we have actually the inertia reference frame. So when applying the equation of motion, it is important that the acceleration of the particle be measured with respect to reference frame that is either fixed or translates with a constant velocity. So in this way, the observer will not accelerate, and measurements of the particle's acceleration will be the same from any reference of this type. So such a frame of reference is commonly known as a Newtonian or inertial reference frame. So this is an example of, this is an illustration of the inertial frame of reference. So it is represented by the X and Y axis. So for this one, when studying the motions of rockets and satellites, it is justifiable to consider the inertial reference frame as fixed to the stars. Whereas since we're talking about dynamics problems concerned with motions on or near the surface of the Earth may be solved by using an inertial frame which is assumed fixed to the Earth. Even though the Earth both rotates about its own axis and revolves about the Sun, the accelerations created by this rotations are relatively small, and so they can be neglected for most applications. So in general, when we consider the inertial reference frame for a particle, especially for dynamics problems, we actually assume that the Earth is always fixed, meaning that since we all know that it rotates about its own axis and it is revolving around the sun, so the rotations and its revolution is relatively small, and this small value can be neglected for the applications in dynamics problems. So that's why the Earth itself will be considered as our Newtonian or inertial reference frame for dynamics problems. Next, for the dynamic equilibrium. As you can see here, this is actually the equation when we define dynamic equilibrium. So the Newton's second law can be written in the alternative form, that is a summation of all forces minus ma is equal to 0, which expresses that if we add the vector negative ma to the forces acting on the particle, we obtain a system of vectors equivalent to 0. So here in the diagram, since in a particle, there are actually forces acting on the particle, and if we add the vector negative ma, the sum, the sum including the summation of all forces is equal to 0. So technically, the dynamic equilibrium is just the alternative form or the other form for the Newton's second law, which is the summation of forces is equal to ma. So we just transpose the ma to the other side of the equation, which it becomes the negative ma. And the vector negative ma of magnitude ma and of direction opposite to that of the acceleration is called an inertia force vector. So the particle may thus be considered to be in equilibrium under the given forces and the inertia vector. If it is treated in the same way as a force vector, then the state of equilibrium created is referred to as the dynamic equilibrium. So this method of application rather, is often referred to as the D'Alembert principle, named after the French mathematician Jean-Laurent D'Alembert. If the particle is said to be in dynamic equilibrium, then the problem under consideration can be solved by the methods developed earlier in statics. So actually in statics of rigid bodies, what we actually use is a summation of all forces is equal to 0. So for dynamic equilibrium, that is, you just only add the vector negative ma, and it will result into, or it is equivalent rather into 0. So that is the definition of the dynamic equilibrium, which is the summation of forces minus the product of mass and acceleration is equal to 0. Next is for the equation of motion for a system of particles. So the equation of motion will now be extended to include a system of particles isolated within an enclosed region in space, as shown here in this figure. So in particular, there is no restriction in the way the particles are connected. So the following analysis applies equally well to the motion of a solid, liquid, or gas system. So at the instant considered the arbitrary I particle, which is represented by a letter I, here in our figure, having a mass mi is subjected to a system of internal forces and resultant external forces. The internal force represented symbolically as small letter fi is the resultant of all the forces the other particles exert on the ith particle. And the resultant external force capital Fi represents, for example, the effect of gravitational, electrical, magnetic, or contact forces between the ith particle and adjacent bodies or particles not included within the system. So the free body and kinetic diagrams for the ith particle are shown below. So this is the FBD and the kinetic diagram of the ith particle. And when we apply the equation of motion, which is the summation of all forces is equal to ma. So the summation of all forces is the external force, which is the capital Fi, plus the internal forces, which is the small letter Fi, is equal to mi times ai. When the equation of motion is applied to each of the other particles of the system, similar equations will result. And if all of these equations are added together vectorially, we obtain the following expression. So the summation of the internal forces, if carried out, will equal 0, since internal forces between any two particles occur in equal but opposite collinear pairs, and consequently, only the sum of the external forces will remain. So if Rg is a position vector which locates the center of mass g of the particles, then by definition of the center of mass, which is the mass times the Rg, is equal to the summation of mi times Ri, where the mass is equal to the summation of mi, or is the summation of all or the total masses rather of all the particles. And differentiating this equation twice with respect to time, assuming that no mass is entering or leaving the system, yields the following expression. So that is the mass times the acceleration that is located at the center of mass g, which is equal to the summation of mi times ai. And thus we obtain the following. So we have here the simplified equation. So this one, it is actually the same on the equation of motion discussed earlier, but the difference here is the acceleration, which has the subscript of g. So we have here the summation of all forces is equal to the product of mass and the acceleration, which it is located at the center of mass g of the particles. Hence, the sum of the external forces acting on the system of particles is equal to the total mass of the particles times the acceleration of its center of mass g. Since in reality, all particles must have a finite size to possess mass, the equation justifies application of the equation of motion to a body that is represented as a single particle. So in general, the equation of motion for a system of particles is the expression which enclosed by a box or by a square rather. So that is the summation of all forces, which are the external forces, is equal to the total mass of all the particles times the acceleration of its center of mass g. So you can actually base that from the illustration here on the right side. So that would be all about the equation of motion, the dynamic equilibrium, and also applying equation of motion for a system of particles.